Okay, it's 9 a.m. Let's get started. Hi everyone, thank you for attending this week's Paraton Chemistry webinar. I'm Bo Xiao from UC San Diego, and today's speaker is Professor Gilad Haran from Weizmann Institute of Science. But before we start, I would like to make a few announcements and then introduce the future schedule and mechanisms of this webinar series. So first, there's an advertisement that the Journal of Chemical Physics will have a special issue with the topic Paraton chemistry, molecules and cavities, molecules in cavities and plasmonic medium. And the editors will be Professor Jensen, Professor Shergai, Wei, and Howell. And you're all welcome to submit. So the submission deadline will be on October 16th, 2020. Let's go back to our webinar introduction. So our webinar will be held every Wednesday, 9 a.m. at Pacific Standard Time. For each talk, you must register using the link here or the link we provided in our reminder email that we send out every week. So here's the future schedule of our talks. One thing I would like to highlight is that we'll also extend our webinar invitation to postdocs to our panelists. And our first group of postdocs, Dr. Christine Anadotia from University of St. Andrews and Dr. Bingu from UC Irvine will give talks lasting about 20 minutes for each of them. And the following groups of postdoc panelists will be chosen through an application procedure, and the details of this application process are not yet established, but it's happening soon, and we'll give more details via our social media on Twitter and Facebook. And you can also send us emails to check for details. And also, we recently have created a new Paraton Chemistry online community on Facebook page. You can find it by searching this name. So once you're in, you can share your own papers and also discuss with everyone here. And for our YouTube video channels, we have uploaded all the recorded talks. And if you search Paraton Chemistry webinar, you'll find our channel. And here's all the videos for you to rewatch. And don't forget to subscribe. And finally, I would like to explain the webinar mechanisms for new attendees. So during the talk, you can use raise hand button to ask questions, and I will interrupt our speaker in the appropriate places and enable your audience for you to talk. And you can also type in your questions or comments using the chat, and then you can discuss with everyone here. And for Q&A, you can write down your questions, which will be raised by the end of the presentation. And for the questions that are not addressed in the webinar due to a time limit, we'll collect them and send them to the speaker later. Okay, let's move back to today's webinar. So our speaker today is Professor Gilad Haran from Weizmann Institute of Science. Professor Haran was born in Holon, Israel, and earned his bachelor's degree from Hebrew University of Jerusalem School of Medicine in 1986. He then completed his graduate studies at Weizmann Institute of Science and received his PhD in 1993. And following his postdoc research at University of Pennsylvania, he returned to Weizmann Institute in 1998 and joined the Department of Chemical Physics. Professor Haran is the recipient of a 2017 advanced grant from European Research Council. He was awarded the 2017 Weizmann Prize and also the 2019 ACS Physical Chemistry Division Award. The research in his group has three major directions: single molecule protein dynamics, coupling quantum emitters and surface plasmons, and also super resolution microscopy of the cell membrane. So today, Professor Haran will give us a talk entitled Observing Strong Coupling in Plasmonic Cavities at Single Emitter Limit. So with all the introduction, let's move the stage to Professor Haran. Professor, now you can share your screen.
Okay, thank you very much. It's a real pleasure to talk in this webinar series. I've been following this series since it began, and I must say it's an exquisite opportunity to learn a lot of new things. I would like to thank you, Bo, and also Wei and Joel for early on starting this community service, which is really fulfilling a thirst in the community, and you can see that by the number of participants that join these lectures every week. So today I would like to share with you some of our work on strong coupling in plasmonic cavities using single quantum emitters or using several quantum emitters close to the single emitter limit. And basically the idea behind using plasmonic systems in order to look at strong coupling phenomena stems from the fact that when we look at aggregates of plasmonic particles, we know that they can form what some people call antennas, but in fact are nothing but cavities, because they can confine the electromagnetic energy into gaps between particles. And you can see here a potpourri of different arrangements of particles. In each of them, there are particular modes that they can sustain. And all of these modes are actually characterized by the fact that you will have some points within these arrangements where the electromagnetic field is particularly strong. So focusing on a specific form of a plasmonic antenna or cavity, which is the bowtie cavity. This is a bowtie made of silver. Its size is about 80 nanometer. We are going to see many of these during the talk. So this is the lowest energy excitation of such a plasmonic cavity, and it involves this kind of arrangements of charges in the cavity. And you can look at it as the formation of two dipoles, one in each particle, and these dipoles coupled together. There is another arrangement, which also has a low energy, not as low as this one, but it also leads to a mode, and that is this mode, where the two dipoles are now inverted. And the reason this is interesting is because I'm just going to, I'm sorry, I'm just going to look at the regular arrow. Can you see? I hope you can see this arrow too. So the reason I'm going to highlight this mode as well as this mode is because in this case, the sum of the dipoles is positive, which leads to a bright mode, while in this case, the sum of the dipoles is 0, which means that this arrangement does not actually radiate to the far field. We will see that we are able to connect to it in the near field, but we will get to that in the last part of the talk. As I said before, a property of all of these arrangements of plasmonic particles, and certainly the bowties, is that in the gap between the particles, there is a strong electromagnetic field, and we would like to use this electromagnetic field in order to couple to quantum emitters. So this is the project that I'm going to describe to you, how we couple quantum emitters into bowtie plasmonic cavities and what we find when we do that. This is a project that was started in the lab some years ago by a postdoc called Santosh Kotny. He has already left the lab. And it's been continued by Dr. Rabi, by Dr. Satyendra Gupta, and by my colleague from the Technion, Dr. Lev Chumtonov, who has been our partner in this project for many, many years. So let's talk a little bit more generally about cavities and about the coupling of quantum emitters to cavities. This is the field that is called cavity quantum electrodynamics. So here's a schematic of a cavity. In this case, it's a large cavity made of two mirrors. And we have a quantum emitter sitting here in the middle of the cavity. Let's see how the energy levels of this arrangement can be described. This is, of course, very familiar to all the participants of this webinar. So we have a cavity mode, and we have the excited state of the quantum emitter, and there is coupling between them, which leads to splitting. So we form two polaritons, lower polariton and upper polariton, that are separated by twice the coupling. In terms of the spectra, if we have a spectrum for the emitter and a spectrum for the particle, they combine together, and we get a split spectrum that will have this typical form. And this is, of course, called vacuum Rabi splitting, because it occurs, if we look on the typical Hamiltonian that describes such phenomenon, it can occur in the absence of photons in the cavity. So it's a vacuum phenomenon. Okay, so let's see how that looks. So this is a very classical example back from 2004. This is a photonic crystal cavity. You can see the cavity here in the center. And there was a quantum dot, a self-assembled quantum dot within this cavity. And you can see here that in the spectra, there is indeed this hole that is a hallmark of vacuum Rabi splitting. And this occurs in a very robust manner in the photoluminescence from this quantum dot. But you have to notice that this is an experiment that was done at cryogenic temperatures, and all the lines, all the line widths of the different constituents of this experiment are very narrow. You can see it here, the wavelength range is very, very small. So we would like to be able to do the same with plasmonic cavities, which are much broader in their spectra, and with quantum emitters that are broader as well. And we want to do that at room temperature. Before telling you how we do that, let's look at the parameters that are typical of such a system. We already discussed the line widths. So we have a line width of the cavity, which we call kappa, and we have the line widths of the quantum emitter that sits here, which we call gamma. And of course, we have the resonant frequencies of the emitter and of the cavity. This is a general cavity, of course, but the same will also pertain to the bowtie cavity that we are talking about here. So we have the coupling constant, G, and in order to have strong coupling, of course, we need G to be of the order or larger than these line widths. And in physical terms, what this means is that when the emitter emits a photon, the photon bounces in the cavity at least one time, or even better, several times before it escapes. And that is the description of strong coupling between the emitter and the cavity. Now, there is one description of the cavity that is quite often used, which is called the quality factor of the cavity, and it is the ratio between the resonant frequency of the cavity and kappa. And this basically tells us how many times a photon will bounce in the cavity before it escapes. So it's very important. And of course, people who work in the quantum QED, the cavity QED community usually work with cavities with very high Q. The other thing that we need to think about is that the G, the coupling strengths, depend both on the dipole moment of the quantum emitter and on the electric field that the quantum emitter sees. And this electric field depends in turn on the volume of the cavity or on the volume of the mode in the cavity. So this leads to the fact that we need to think not only on the quality of the cavity, but also on its volume or its mode volume. And this brings us to, again, to plasmonic cavities. Plasmonic cavities typically have pretty low quality factors, and this is because of the strong losses of the metallic particles. On the other hand, they also have very small volumes. And this is seen here in this cartoon, two particles with a small gap between them that is encompassed by a molecule. And so you can imagine that the volume here would be very small. So this leads to a very high figure of merit because Q over V is going to be large. And this means that we can attain the strong coupling limit, even though the quality factor is not very good. So coming to the system that we are working on, as I said, bowtie cavity made of silver, and we would like to insert quantum dots into this bowtie cavity. Why are we interested in using quantum dots? The reason is because the typical colloidal quantum dots have large oscillator strengths than compared to molecules, which means that it will be perhaps easier to couple them to the plasmonic cavity. And also they have a much higher photostability compared to molecules, which implies that we can collect more photons from such a quantum dot than we can collect from a molecule before photobleaching. Now, there have been many studies on quantum dots in relation to plasmonic particles and how they couple, especially in the weak coupling regime. You can find more information on that in the review that we wrote last year, and you can see the reference on the bottom. But I want to mention that in the framework of this talk, we are interested in looking at a very small number of quantum dots, and we would like to push to the strong coupling regime. So here are the ingredients of our experiments. So this is again the bowtie. I showed you the bowtie in the beginning. You can see the typical size here from the scale. And this is the spectrum of scattering from such a bowtie. And kappa is indeed very large, about close to 400 milli-electron volts. This is the quantum dot that we're using. It has a resonance around 650 nanometers, and the line width corresponds to about 130 milli-electron volts. So with these ingredients, we would like to prepare our system. How do we do that? Just very quickly, we developed a process that involves several electron beam lithography steps, whereas we prepare the bowtie on a surface, we cover it with polymer, we dig a hole in the polymer, and then in a solution-based process, we allow quantum dots to insert themselves into the hole. So this leads to bowties with quantum dots that look like this. So you can see several examples. Here's an example with a single quantum dot inside the cavity. Here is an example with two quantum dots, and here is an example where there are several quantum dots in the cavity. We do not fully control the number of quantum dots in the cavities. We can just try to get as low a number as possible. And then the advantage of this experiment is that after we do spectroscopy, we can go to the electron microscope and do what we do here. In other words, take an image of our bowties and actually count the number of quantum dots inside. So this gives us a high level of assurance that we know exactly what we looked at or what we measured with our spectroscopy. Okay, so what do we get? So here are two examples of spectra, scattering spectra that we measure from individual bowties with quantum dots inside. In this case, we have two quantum dots, and in this case, three. And you can see that the spectra show the typical splitting that one would expect to see under a strong coupling regime or close to the strong coupling regime. Now, the black line here is the experimental data, while the colored lines come from a fit to the data based on the coupled oscillator model. So this is a very simple model that assumes that each of the ingredients of the system is a harmonic oscillator, and one couples them and one drives them with the electromagnetic field from outside, and then this model can be solved. And this is the typical expression that one gets for scattering from such a coupled oscillator. You can find more information in this paper on the bottom. And as before, the parameters of this system are the resonant frequencies, the line widths, and the coupling strengths, just like we discussed before. So back to the spectra, we fit each spectrum with the solution to the coupled oscillator model, and we can extract parameters like the G that characterizes each of these spectra, which is what we really want to learn about. So now here are two examples where we have only one quantum dot in the cavity. And this is a little bit more tricky because you can see that the dip in the spectrum is a bit smaller in this case. And in the second case, we don't even really see the dip so much in the spectrum, but in fact, the spectrum is significantly broader than the spectrum of an empty bow tie. So we know that something starts to happen here. So with a single quantum dot, we are not quite at this strong coupling regime, but with several quantum dots, we see that the dip in the spectrum is more developed. So how do we know that this is indeed due to the coupling between the quantum dot and the bow tie? We can use polarization spectroscopy. So obviously, the coupling will be strongest when the polarization of the light is along the direction of the bow tie, along the direction which we mark as 0 here. And then we can try to tune the polarization away from that direction until it is 90 degrees off. And you can see that the dip in the spectrum gradually goes away. Now, of course, there is still a resonance here, which is due to the individual particles. Even if we are at 90 degrees, there is a plasmonic resonance in the system. That's what you see here, but there is no dip due to coupling anymore.
Professor?
Yes.
There's a questions. I will
Sure.
enable the audio.
Okay.
Yeah. Also, you can ask your questions.
His microphone is mute. Oh, there we go.
You can mute.
Yeah. It was an accident. Sorry.
Oh, it's an accident. Okay. So, do you have a question for now? Okay.
No, I guess not.
Yeah.
Okay.
Sorry, it's an accident.
Okay, so we can compare the results that we get from a series of such measurements to what we expect to get from theoretical or numerical calculations on such systems. And you can see here the calculations for the case of a single quantum dots and two quantum dots. And there is a difference if the quantum dot is in the middle of the cavity or it's close to one of the particles. So we present here two different lines that provide the two different possibilities. And here are the results from our measurements. So we see that there is a qualitative agreement between what we get in the experiment and what we expect to get based on these calculations. Now, this is a good point to say a few words about the onset of the strong coupling and about criteria for reaching the strong coupling regime. So in principle, the two polaritons, the P plus and P minus polaritons, can be described with this simple equation where we have the resonant frequency and then we have this square root factor that includes the coupling and includes also the line widths of the two systems. And in fact, yes.
Sorry to interrupt. There's questions from Yeah.
Well, hi, Gilad. Sorry, this is Joel Yun from UCSD. I have a very naive question. So when you were showing the spectra where you go from the molecules that are, the quantum dots that are polarized with respect to the mode and the ones that are unpolarized, sorry, in the next few slides, yeah, here. So I'm a bit confused because I would assume that the quantum dot has isotropic dipolar, basically it has dipoles across all x, y, z. So why wouldn't why would it depend on why is there a dependence on the why is there a dependence on the coupling? Isn't the quantum dot isotropically
okay, so let me explain. So basically, as I showed in the beginning, we are talking here about coupling to the bright mode of the bow tie,
yes.
Which is polarized along this direction. So in order to get a strong electromagnetic field in the gap, which is strong enough, remember that the coupling is mu times E, so E has to be strong enough in order to couple to the quantum dot. And E is strong enough when we are exciting this longitudinal plasmonic resonance. If we are exciting the other resonance of the particles, E in the gap is just not strong enough for this coupling. So that's why we don't see it.
Okay, but there is always a dipole that is pointing along, say, the electric field of that mode anyway, yes. Right? Okay, yeah. Thank you. Okay, so this is an excitation. Okay, thank you.
Okay, so back to this expression for P plus and P minus. This expression can be described in graphical terms in this way. So if G is too small, we have just a single branch. We don't have yet P plus and P minus. But when G becomes larger, G squared becomes larger than kappa minus gamma squared divided by 16, then we start to have these two branches, P plus and P minus. So we can put the parameters of our system, kappa and gamma of our system, and compute that G has to be larger than 65 millielectron volts to be beyond this point and start to have the two branches in the spectrum. But in fact, this is not enough in order to see two real branches in the spectrum, because there's another dependence on the line width of the spectrum, which might mask the two branches and make them look as if they are a single branch. And so people sometimes also use this criterion where G is now bigger than the sum of kappa plus gamma divided by 4. And if we put our numbers here, we get strong coupling only when G is about 130 millielectron volts. However, when we start plotting coupled oscillator derived spectra, and we increase gradually G in these spectra, you can see that much below 130 millielectron volts, we already start to develop a nice dip in the spectrum, which suggests that the strong coupling regime is starting to develop already when we approach perhaps 85 or 100 millielectron volts of coupling between the particles, which is more or less what we have here, at least in the case of some of the particles, and certainly in the case of two quantum dots in the cavity. Okay, so let's continue. Summarizing this part of the talk, what I showed you is that we can generate bow ties with cavities that form cavities with a high figure of merit. Q over V is fairly large, and this is because V is very small and not because Q is large. The quantum dots can be inserted into the cavities, and as I mentioned, it's nice that we can count them by electron microscopy, and we can tell exactly how many quantum dots we have. And strong coupling can then be achieved, certainly with a few quantum dots, and perhaps even in the limit of a single quantum dot. And we see that as Rabi splitting in scattering spectra. Now, can we see that also not only in scattering spectra, but also in other types of spectroscopy observables? And of course, what jumps into the mind is photoluminescence. And in fact, in this scheme, which is similar to the scheme that I showed you before, one might imagine that there will be photoluminescence from the two polaritonic level, P plus and P minus. And one should be able to see also splitting in the photoluminescence spectrum. And indeed, in 2018 and a bit later, there were two examples in the literature of such splitting in plasmonic strong coupling PL spectra. This is from the group of Bert Hecht. And you can see this is a bit more complicated than the single splitting that I showed you before, because a more complex excitation of quantum dots is involved here. And another example from Matthew Pelton's lab, also coupled quantum dots to a plasmonic cavity. And you can see here in blue the scattering spectrum, and in green the PL spectrum, and you can see the similarity between them, which suggests that this is indeed what they see here, the formation of strong coupling through the two types of observations. So we decided to do the same and to look on PL in our spectra. And so here's an example of a bow tie.
Sorry to interrupt. There's one more question.
Sure.
Hi, Gilad. Hi, Gilad. Yeah, this is Randall Goldsmith at UW-Madison. Nice to hear your voice. So you showed this nice analytical form a couple slides ago that matches your data. And I wanted to know that if you added another interaction in the analytical form that captured a near-field coupling between the individual quantum dots, not just the coupling to the cavity, how does that change the calculated spectrum, and can you read that out experimentally with either the photoluminescence you're talking about now or the other measurements you were talking about a few slides ago?
So in principle, the standard description of such systems of emitters coupled to cavities, which is embodied in the famous James Cummings Hamiltonian, shows that in fact the coupling of n particles to a cavity, the strength of that coupling goes like square root of the number of particles. So that's how it builds in. And in principle, we should be able to see that by looking, let me go back, by looking at these curves. So in fact, the numerical curves would show this relation. So for 2 particles, you will have square root of 2 as much coupling as for 1 particle. But we don't see that too much in the results yet here, because there is also noise due to the position of the quantum dots inside the cavity. So
but you're talking about interactions just between the quantum dots in the cavity. If the quantum dots, there's 2 of them in there and they're also strongly interacted with each other, then your Hamiltonian changes.
Don't interact very strongly with each other because they are too large. The distance between them is such that you do not expect a strong coupling between 2 quantum dots, perhaps through the cavity, but not in free space. So 2 quantum dots in free space do not interact with each other strongly.
Thanks.
Okay, so here's an example where we look at scattering from a bow tie with a quantum dot or several quantum dots, and we see a dip in the scattering spectrum, and we see also a dip in the photoluminescence spectrum. And the dashed curves just show the original spectra before coupling to the quantum dots. Here's another example. Again, dip in the scattering spectrum, dip in the photoluminescence spectrum. So that looks nice, except that we got quite puzzled when we tried to plot the 2 types of spectra on top of each other. And we realized that the photoluminescence spectrum looks much narrower than the scattering spectrum. In fact, when we looked at the splitting in the PL spectrum compared to the splitting in the scattering spectrum, we found, to our horror, that the PL splitting does not correlate at all with the splitting in the scattering spectrum. So we scratched our head quite strongly in order to try to understand what's going on here. And we tried to first do another set of measurements in order to see what kind of system exactly we are looking at. And one way to look at quantum emitters inside cavities is by following or probing the non-classical nature of the emission from these particles. And this can be done through the phenomenon which is called anti-bunching, the fact that 2 photons cannot be emitted at the same time from a single emitter. And we can measure that using the famous Hanbury, Brown, and Twiss experiment, where you take the light from the sample and you split it on 2 detectors, and you look on the coincidence between counts on the 2 detectors. And basically you ask the question, if I just counted a photon on detector 1, what is the probability that at the time t after that I will find a photon on detector 2? And as I just mentioned, anti-bunching means that at time 0, you do not expect to have 2 photons. Here's how it looks. This is the correlation functions from a single quantum dot inside a plasmonic cavity. And you can see that at time 0, the correlation goes almost to zero. There is some noise in the system, so it doesn't go completely to zero. But in fact, theory tells us that the correlation at time zero should go like 1 minus 1 over n. N is the number of particles in the cavity. So if we have one particle, we should expect to get zero. If we have two particles, we should expect to get half. So you see that the peak here is way below half, which implies that indeed we have a single particle. This is another case where we have 3 quantum dots, and you see that the peak is much smaller, but still within the limits expected for 3 quantum dots. Now, one thing in addition to the position of the peak at zero that we can get from such spectra is the lifetime of the quantum dots, because the decay here matches the decay that we expect for the photoluminescence due to radiative emission from the cavity. So let's see how this looks. So first, a quantum dot in free space on glass, not in a cavity. And from fitting the correlation function, we find that the lifetime is about 20 nanoseconds. And then we looked inside the cavity, and we find that the quantum dot lifetime in this particular case is around 11 nanoseconds. In some cases, we get 5 nanoseconds or a little bit below that. So we get just a factor of 2 to 4 below the free space number. This is again puzzling, because we expect that the coupling between the quantum dot and the cavity will lead to a shortened lifetime that is closer perhaps to the lifetime of the plasmon in the cavity, and we don't get anything close to that. So we have 3 puzzling observations here. The photoluminescence line seems to be too narrow. The splitting is independent of scattering splitting, and the lifetime is too long. So in order to try to understand that, we looked at the literature at the excitations of quantum dots, and at some point we realized that in fact quantum dots are not the 2-level systems that one might think are useful for description of what we discussed so far, but are much more complicated in terms of their excited state levels. And in fact, one of the properties of quantum dots is that they have some dark states, and one of the most famous dark states is a dark state due to trapping of electrons on the surface of the quantum dot, which leads to a very long lifetime and can be seen in specialized experiments. So we thought maybe some of these excited states that beyond the typical lowest level excitation are involved in what we see here. And we turn to our friend Javier Aizpurua from San Sebastian. And Javier, together with his PhD student, Thomas Neumann, who is now a postdoc at Harvard, and you can often hear him asking questions in this webinar series, and together with Ruben Esteban, they set about to simulate the system and to see whether addition of dark states into the description can explain the results that we see. So here's how they envisioned the system. So we have here the plasmonic bowtie with its own excited state, and we have the quantum dot. And now we simulate the quantum dot with 2 different excited states, not only the bright state that we described so far, but also the dark state that I just introduced. And the different arrows are the different relaxations of both the plasmonic system and the quantum dot system. And of course, we have coupling. We have the regular coupling between the bright state and the cavity, but we also have weak coupling between the dark state and the cavity. So the dark state can also couple to the cavity in this model, but only weakly. So since we have this description, we or actually Thomas writes an Hamiltonian and then solves it and computes the different spectra that we measure. So the first spectrum to compute is the scattering spectrum. So Thomas took typical parameters from our experiments, and this is how the scattering spectrum looks. And you can see nicely the dip due to coupling. And here's the PL spectrum. And the PL spectrum looks just like we expected it to look. Well, this was done after many iterations by which we tried many different arrangements, and we eventually got to the arrangement that I just showed you. And then indeed, the PL spectrum looks narrower than the scattering spectrum. just like we wanted it to be based on the experiment. And the question is, what do we have here? Well, Thomas actually very excitedly told us when he did that, that in fact, what you see here is that two peaks, but the two peaks are due to different things. There are not two polaritons. And in fact, the narrower peak here is due to the dark state that I just mentioned before. How do we know that? How does Thomas know that? Let me show you how one can build the spectrum step by step in the simulation. So of course, in the simulation, you can actually turn off the coupling of each of the components. For example, the dark state. So here, the dark state coupling is turned to 0. And so this is the spectrum that one gets, the PL spectrum. So the PL spectrum does not show a splitting, but its line width is actually about twice as broad as the spectrum of the PL of a free space quantum dot. So there's already something happening in the PL spectrum due to the coupling to the cavity. Then let's look what happens if we turn off the coupling of the bright mode and leave only the coupling of the dark mode. And in this case, wow, we get a narrow spectrum here, which shows that the very weak coupling of the dark state to the cavity is enough to increase its emission significantly and create a narrow line which looks like this. And now what happens with both GD and GB turned on? This is now the red line that you see here with the two peaks. So the two peaks do not directly add together. It's more complicated than that. I don't want to get into the description, but they actually form this kind of complicated spectrum, which now includes two different types of phenomena. So what we have here is that the plasmonic cavity enhances the dark state so significantly that the emission from this dark state becomes significant and leads to this complex spectrum that we see. Now, what about the correlation function? Correlation functions can also be calculated from the model that Thomas wrote. And so the surprise here was that the correlation function has two components. One is a very fast component and another one much slower. And in fact, this fast component, we cannot see it at all in our experiment because our time resolution is not good enough for that. And it's on the femtosecond time scale. While the slow component is what we see in the experiment. And this leads, basically, it closes the story of the three puzzles that I showed you, because now we understand exactly what happens here. And we understand that basically all the emission features that we see here are due to this complex interplay between two states of the quantum dot, the bright state and the dark state, each of them coupled differently to the cavity, and each of them leading to its own contribution to the photoluminescence, both in the spectra and in the correlation function.
Professor?
I would like to also remind you again that the correlation functions tell us that the light from the cavity is non-classical. So we really see individual quantum dots in the cavity. We can count them using this phenomenon as well. And we can compare it to what we get from the electron microscope, and we find good agreement. I don't have time to show you that agreement here. So finally,
Professor?
Yes.
Sorry to interrupt. There are two questions. I will allow them to talk.
Please.
Matt, you can.
Hi, I have a question about the coupling between the dark state and then the plasmon mode. So when that coupling occurs, why does the line width narrow?
Of the dark state?
Yeah.
You mean this one?
Yes, yeah.
Yes, so the line width is narrow because the dark state relaxation is relatively slow. So if you so that's part of the model basically, and it matches what we know, as I showed you before, what we know from the physics of dark states in quantum dots. These dark states, which are due to trapped electrons, have very long lifetimes. So the long lifetimes would correspond to relatively narrow line widths.
Oh, so okay, I guess I misunderstood. So the yellow represents the bright mode and the...
So the yellow is the bright mode.
Oh, okay, I'm sorry, I misunderstood. Okay, and actually I have another question. So regarding the dark plasmon mode, do you know if that has any role, plays any role in the dynamics or the photoluminescence?
That's the next part of the talk.
Okay. I'll wait. Thank you.
Yes.
Yeah, we have another question. Okay. Oh, another two actually. So Matt, if you okay.
Okay.
Yeah, where you can talk.
Hey, Gilad, very nice. I have a quick question. So what's the source of the dark mode coupling here? So I guess it must be some breaking down of the dipole approximation. Do you have any ideas here?
So I'm sorry, can you repeat?
Yeah, so I'm just wondering what is the source of this dark mode coupling? Is it the dipole interaction or quadrupole?
Oh, that we don't really know. I can imagine that the dark mode is, well, since if you imagine that it's an electron trapped on the surface of the quantum dot, then it's not really going to be a simple dipolar mode, but in the Hamiltonian that is written for the simulation, it's just simple dipolar coupling.
Okay, I see. Thanks. Actually, just follow up something up. So if it is really a surface trapping mode, do you guys think you can control the surface chemistry of the ligands? I know some ligands are more prone to have trap state, some ligands are less, and examine see if the contribution of the dark mode can become bigger or smaller.
Yes, in principle, one might think about ways to do that. Our particles, the quantum dots that we're using, are commercial particles, so we're not really touching their surfaces. So that would be, we have to teach ourselves how to create the particles in the lab, or at least how to change their surface chemistry. We haven't done that so far.
I see. Thank you.
Yeah, there are a couple of more questions. Yeah, sorry for the interruption.
Sorry, Gilad. So I think I understood your explanation of why the PL looks like shrunk. But then what I don't understand is, did you already explain why the scattering spectra has the peaks that do not correspond to this bright and dark mode? Maybe I missed this.
So the scattering spectrum actually fields earlier. If you start to increase G, the scattering spectrum will always have a deeper dip in it. And the reason for that is partly because in the scattering spectrum, you also get some interference between the modes, which usually leads to a more developed dip than you would see in the PL. So
wait, but then the Rabi splitting of their scattering spectrum, so is that related to polaritonic features, or what is that related to?
Yes, definitely. That's purely due to the polaritonic effect with some interference between the modes, which leads to a slightly deeper spectrum than you would expect just based on the polariton. So it's not a good practice, for example, just to measure the difference between these 2 points and to say that this is the Rabi splitting, because it's a little bit more complicated than that, but it's approximately correct. So you can actually see what the splitting is based on that.
Okay, but sorry, but I just have one more question, but I still don't understand then how come when you presented a very compelling model by Thomas Newman on how the PL can be completely explained by that model, but I don't see how that model explains the scattering spectrum.
Well, the model actually has all the components for the scattering as well. The scattering is just due to the coupling between the plasmonic cavity and the bright mode. So in fact, the dark mode does not play any role in the scattering spectrum. It just
but then in the PL, but then how come in the PL does the bright mode show up not Rabi split? Why is it just showing up like centered at the bright
because
resonance?
in the you can measure kind of late photons that are emitted also by the dark mode, And this, the dark mode does not contribute to the, I mean, the dark mode is also coupled to the cavity only weakly. So the dark mode would not lead to any splitting in the scattering or any additional splitting. And so any contribution from the dark mode would be completely hidden here.
Sure, but then the bright mode, in your explanation seems not shifted in energy when you calculate the photoluminescence.
Yes, that's right. So the bright mode, as I mentioned, the bright mode is still not fully developed to show a splitting here, but it's already much broader than the bright mode outside the cavity.
Okay, I think I'll ask you later, but I'm still a bit confused about that point. Okay, sorry about that. Okay.
Okay, next.
Okay, another question?
Yeah.
Oh, hello?
Yes.
Oh, yeah. So a naive question. You said that the photoluminescence spectrum can be understood in terms of the dark mode of the quantum dot.
Yes.
So my question is just, do you know what is the mechanism that fits population into that mode once that you populate the polarity modes? Is just due to phonons, or it's another?
So we can only guess based on the literature of quantum dots. And our guess involves trapped electron states on the surface of the quantum dots, but we don't know for sure because we don't yet have a way to directly test that. We are thinking about ways to do that in the future.
Oh, okay. Thank you.
Okay, shall I continue?
Yeah, there are two more questions. Sorry, people are very interested in this part. Yeah, John, you can talk.
Well, yeah. So I have a kind of question regarding this this dark state as well. So, I guess what's the rationale behind it being a charge separated like surface trap state as opposed to, and then on these CAD cell zinc sulfide quantum dots, the exton fine structure generally has splittings between, there's dark and bright slates that are based on angular momentum, and there's also spin forbidden transitions as well that have.
That's a very good question, actually. So yes, you're right. There are additional dark states in quantum dots, but these dark states are always separated from the bright state by less than 10 milli-electron volts. And so people usually see them when they cool down quantum dots to cryogenic temperatures. But at room temperature, this difference between the states is just not enough to be seen as separate peaks in our spectrum. So we need to at least include a splitting of 50 milli-electron volts between the bright and the dark state. Otherwise, we will not see the two separate spectra. So 50 milli-electron volts is just too much for the type of dark states that you mentioned.
Okay, I'll agree with that for now.
Okay, one last.
Hello?
Yes.
Yeah.
Hi. I just have a question about your G2, the one that you measured for the 3 quantum dots. So if I understood correctly, your explanation is that it is predicted that it will have a fast component, very, very fast component that you cannot measure, and that's why you have a G2 that at 0 time is greater than 0. So my question is, what is the time scale of that fast component? Because I cannot see it in that time scale of the nanoscale.
Yes, that's right. I should have presented it in a way that you could see it. It's on the femtosecond time scale.
It's on the femtosecond time scale. And what is the explanation for that fast component? What is it associated to that femtosecond time scale?
Is basically due to leaking of photons from the cavity through the plasmonic mode. So the plasmonic lifetime basically dictates the lifetime of the fast component.
I see. Yeah. I just have a doubt because I know that when you have 3 emitters that are independent, you will have a G2 in which at 0 time is greater than 0. So I was wondering if that was what's happening in your case. But you say that this is in the femtosecond time scale and that is limited by the plasmonic.
The issue is not just the dip at time 0, but also the lifetime of what we see.
Ah,
right?
okay.
So the lifetime is too long. What we see is just this lifetime that I plot here.
Okay.
We never see this past lifetime here. And by the way, we know when we have a single quantum dot, even in that case, we get very low, very long lifetime, and we don't get the fast component.
Okay, got it. Okay, great. Thank you.
Thank you.
Well, thank you. That's the last one. You can continue.
Okay, so in the few minutes that are left, let me quickly go through the last part of the talk, and that has to do with the dark mode of the plasmonic bowtie that I was asked about. So coming back to this dark mode, we asked ourselves how we can actually look at coupling between our quantum dots and this particular dark mode. And as I mentioned in the beginning, this dark mode does not radiate to the far field, so we cannot see it using the same type of measurements that we did so far. So we turn to our colleague, Dr. Lothar Huben, who is an expert on electron microscopy, and to a method that involves electron microscopy and that can probe the dark mode in the near field. So this is electron energy loss spectroscopy. Briefly, you have an electron beam that you shine on the system, and the electron beam can couple to the plasmonic system, excite the different excitations of the system locally, and then the electrons, due to this excitation, they lose energy, and you just look at the loss of energy in the electrons that are scattered from the sample, and you get here a spectrum. And this is the spectrum that is called electron energy loss spectrum, and it tells you about the excitations in the system. So starting with the bright mode, it turns out that if we put the electron beam right here in the corner, we can excite the bright mode, and you can see that in this calculation of the charge distribution induced by this excitation. And this is how the spectrum looks like, and you can look only on the lowest energy excitation here, which is due to the plasmonic bright mode. And this is how it would look if we scan our electron beam around the bowtie at different positions, but with the energy that matches this bright mode here. Okay, so you can see that the excitation is strongest when we are at this region of the bowtie, and that's why I put the point here. Now going to the dark mode, it turns out that the excitation is strongest for the dark mode when we put the electron beam in the center of the gap. And in this case, we get a completely different spectrum. The peak is now about 2 electron volts, a little bit above. And you can see that this is the distribution of the excitation around the bowtie, with the strongest point here in the center between the two particles. So now that we know how the EELS maps and the EELS spectra look like, we can start to put quantum dots inside. So first we looked at the bright mode, the same quantum dots that we had before. We did not dare to look at the level of small number of quantum dots, so we put a lot in the beginning, and we put our laser beam, our electron beam here, and here's the spectrum that we get. So lo and behold, we see a splitting in the spectrum as before, and again there is a coupled oscillator fit here, and we get G values which are similar to the G values that we get in our scattering experiments. Then we can do the same with the dark mode, but now we shift to another type of quantum dots that has a resonance at 2 electron volts in order to match the dark mode resonance. We put our electron beam in the center, and again we see splitting in the spectrum. So what we see here is that the dark mode actually couples nicely to the quantum dots, but in this case, the quantum dots are in direct resonance with this dark mode. So we tried to calculate this phenomenon, and in this case, Michal Kvapil from Brno University, from the group of Thomas Chikola, spent some time in our lab and did the calculations using the boundary element method. And Michal started by putting 4 particles inside the bowtie, and did the calculation. And surprisingly, there was no splitting in the spectrum whatsoever. So this is the EELS spectrum calculated from the system without any splitting. So Michal came to my office and he said, I don't see any splitting. I told him, why don't you put more quantum dots here? Maybe that will help. So we did the same calculation now with a larger number of quantum dots, but now they don't fit inside the gap anymore. So they are a little bit outside the gap. And now we got the splitting in the spectrum. So that was really nice. But then Michal said, maybe I will try just to leave the peripheral quantum dots in the calculation and take out the quantum dots from the center. And that was a really brilliant idea, because we found that we can get the same splitting even without the quantum dots in the center. So then we started looking at maps generated from the calculation of the electromagnetic field of the dark mode. And then we realized immediately what happened. So you can see here that in fact the electromagnetic field is much stronger at the periphery of the gap rather than in the center of the gap. And this leads to the fact that when we put particles at the periphery of the gap, and this is an example where the particles are not in the center but only in the periphery, in this case we get splitting, even though for the bright mode we would expect splitting to be strongest when the particles are in the center. And there is a dichotomy here, because the particles are in the periphery, but we probe them with an electron beam that sits right in the center. So that's an interesting phenomenon that has to do with coupling of the dark mode. As I mentioned before, we cannot look at the dark mode using our regular scattering spectra, but we can look at the dark mode using electron energy loss spectroscopy in the electron microscope in the near field. And we can actually see that even dark modes can nicely couple to the particles, to the quantum dots, and can lead to splitting in the spectrum. So I will conclude my talk here. I showed you that the onset of strong coupling phenomena between quantum dots and plasmonic particles can be observed at the level of individual quantum dots, at the level of individual plasmonic cavities. I showed you different observables that we can use in order to probe the system, from scattering spectra through PL to electron energy loss. And I showed you that there are several novel phenomena that involve dark states, either of the emitter or of the cavity. And of course, we have a lot to do in the future. We would like to improve the coupling between the bow ties and the quantum dots. We would like to find some interesting quantum optical applications, and perhaps in the very future, very far future, we might move to molecules again instead of quantum dots, and perhaps then see a new set of interesting phenomena that might arise in that case. So I would like to thank the people who were involved in the work. I already mentioned most of the people. I would also like to mention Dr. Inbal Riven, my lab manager, and several sources of money for this work. And I would like to thank you for listening and for asking questions, and I will be glad to answer additional questions if there are any. Thank you very much.
All right, thank you. So let's see if we have any questions.
Hey, Gilad, I just have a quick clarification about the last part. So for the EELS spectrum excitation, for the bright mode, you excite on the outside, but you still have the quantum dots at the tip in the gap, right? And that's where that you have the strongest field enhancement.
Yes.
Okay. Okay. Thank you.
Yeah. So that's an interesting phenomenon of this EELS excitation, that the laser, sorry, I keep saying laser instead of electron. The electron beam is not at the same position necessarily where the strongest coupling is.
Okay. So we don't have more questions.
Yeah, no more. No more.
Okay.
Thank you.
Hello.
Yes.
I have a question. Did you try to measure the colloidal while you excited the structure with electron beam?
Sorry, I did not understand your question.
So have you tried to measure the emission of the polariton? Why it's
Yeah, that would be an interesting measurement to do. You can do that, I guess, using photoluminescence, but we don't, unfortunately, we don't have a photoluminescence system on our electron microscope, so we cannot do that right now. Maybe in the future.
So will you think it will be more look like to the scattering spectral or the PL spectral in your previous sections?
So it should look more like the PL spectrum. There is some discussion in the literature about the difference between electron energy loss and cathodoluminescence. I'm not quite sure right now, I don't remember, but if you write to me later, I can point you to the relevant literature.
Okay, thanks.
Okay, next. Massimo, you can start talking. Yeah, you can unmute yourself and then start, ask question.
I wanted to ask you, the search for the strongest coupling. Is this, for instance, this bowtie design, is this the optimum that one can conceive, or do you think there is some other geometry which would be more important? Can one systematically pursue, the raising of the coupling by new and different geometries for the resonant particles?
That's a good question. There's actually an interplay here between several different requirements of the experiment. First of all, we would like to have the strongest electromagnetic field in the gap. But on the other end, since we're using quantum dots, we would like to be able to put the quantum dots in. And the quantum dots that we're using have a size of perhaps 6 to 8 nanometers. So we cannot use a gap that is smaller than that. In fact, we haven't quite arrived there yet, and our gaps are more of the order of 15 to 20 nanometers. So we have a way to go by just reducing the gap size and improving in that way the coupling. But you can think of other arrangements, like, for example, particle on a mirror arrangement, which is something that several people are using, including Jeremy Bomberg, who is going to give a talk next week. And in that case, you can put a molecule inside the gap between a particle and a mirror, and the gap there can be significantly smaller than in our case, meaning that the field is larger. But there are other limitations in that case. For example, you cannot count the number of molecules there, and so on and so forth. So when we think about how to decide on which system to use, we have to take into account not only the question of the strength of the electromagnetic field, but also other experimental questions that have to do with building the system.
Okay, so there's a comments in the Q&A actually from Case Nelson. So he said, in fact, you can see the field profile in structures with micron gaps, and the field is the biggest around metallic edges like fringe fields. Yeah, so I wonder if you have anything to reply to him.
Can you repeat it, because
yeah,
I'm
sure.
not sure I understood your question.
Yeah, so he said, in fact, you can see the field profile in structures with micron gaps, and the field is biggest around the metallic edges like fringe field. Yeah, it's actually a comment, I think.
I mean, electromagnetic fields of near plasmonic particles are usually strongest near sharp tips, like the edges of the bowtie. So in addition to the strong enhancement in the gap, you would also have some enhancement along these corners. And in fact, people have used that. People showed strong coupling even with plasmonic cubes, where you have sharp corners, and other structures like that, where the sharp tips can be used in order to focus the electromagnetic field or confine the electromagnetic field to a small enough space.
Okay,
Did
thank
I
you.
answer the question?
Yeah, I guess that's all. And so if there's no more questions, I would like to put an end to today's webinar. So Professor, can you stop sharing so that I'll share my screen? Okay. Okay, thank you, Professor Haran, for your interesting talk. We really appreciate your contributions to our webinars. And so today we have over 110 attendees from all over the world. And we are very happy to see that more and more people are joining us in this webinar series. And for the next webinar, Professor Jeremy Belberg from University of Cambridge will give us a talk entitled Strong Coupling and Molecular Paratones in Extreme Plasmonics. And don't forget to register using the link. And finally, I would like to thank you all for joining us today, and let's meet same time next week. Thank you. Thank you, Professor Haran.
Thank you very much. Bye-bye.